Hello and welcome. In this video, we'll be exploring a powerful application of differentiation called optimization. Optimization is the process of finding the maximum or minimum value of a function under certain conditions or constraints. Essentially, we're looking for the best possible outcome, whether that's the maximum profit, the minimum cost, the largest possible area, or the smallest amount of material needed for a project. By the end of this lesson, you will be able to understand the key concepts of optimization, learn a step-by-step method to tackle these problems, and apply your calculus skills to solve them. Before we dive into solving problems, we need to understand a crucial concept, the difference between local and global maximums and minimums. Let's look at a function, y equals f of x, over a specific interval from x equals a to x equals b. We know that setting the derivative, dy dx, to 0 helps us find the turning points of the function. These are the peaks and valleys. These points, where the slope is 0, are called local maximums or local minimums. They are the highest or lowest points in their immediate neighborhood. However, they are not always the absolute highest or lowest values the function can take over the entire interval. The absolute highest and lowest values are called the global maximum and global minimum. Notice in this example, the global maximum actually occurs at the endpoint, x equals b. The global minimum happens to be the same as the local minimum. So the key takeaway is this. To find the absolute best solution, the global maximum or minimum, you must always check two places. First, check the stationary points you find by setting the derivative to 0. Second, you must check the values of the function at the endpoints of the interval you're considering. This is a critical step that can't be skipped. To bring structure to solving these problems, we'll use a reliable 6-step method. Let's outline this optimization problem-solving method. Step 1. If the problem involves geometry, always start by drawing a clear diagram. This helps you visualize the relationships between different quantities. Step 2. Create a formula for the quantity you want to maximize or minimize, like area, volume, or cost. It's crucial to write this formula in terms of just one variable, like x, and to determine the valid domain or possible values for that variable. Step 3. Find the first derivative of your formula. Then set that derivative equal to 0 and solve for the variable. This gives you the stationary points. Step 4. Test your stationary point. You can use a sign diagram for the first derivative to see if the slope changes from positive to negative for a maximum or negative to positive for a minimum. Step 5. Now, identify the optimal solution. This means comparing the value at your stationary point with the values at the endpoints of the domain to find the global maximum or minimum. And finally, step 6. State your conclusion clearly in a sentence that directly answers the original question. Let's apply this method to our first example. A rectangular cake dish is made from a 25 centimeters by 40 centimeters sheet of tin by cutting squares from the corners and folding up the sides. Our goal is to find the size of the square cutouts that will give us the maximum possible volume for the dish. Step 1 is a diagram. We have a rectangle, 40 by 25. We cut out identical squares of side length x from each corner. Now for step 2, the formula for volume. The volume of the resulting box will be length times width times depth. When we fold up the sides, the depth of the dish will be x. The original length of 40 centimeters is reduced by x on both sides, so the new length is 40 minus 2x. Similarly, the width becomes 25 minus 2x. So our volume function is v of x equals 40 minus 2x times 25 minus 2x times x. Expanding this gives us 4x cubed minus 130x squared plus 1000x. For the domain, x must be greater than 0 and all side lengths must be positive. The shortest side is 25 minus 2x, so this must be greater than 0, which means x must be less than 12.5. So our domain is between 0 and 12.5. Step 3. We find the derivative. v prime of x is 12x squared minus 260x plus 1000. We set this to 0 to find the stationary point. Solving this quadratic equation, for instance, with a calculator or the quadratic formula, gives two solutions. X equals 5, and x is approximately 16.7. Since 16.7 is outside our domain, the only valid stationary point is x equals 5. Step 4. We use a sign diagram to check if x equals 5 is a maximum. We test a value less than 5, like 1, and find v prime is positive. We test a value greater than 5, like 6, and find v prime is negative. The slope goes from positive to flat to negative, which confirms a local maximum. Step 5. Since we have an open domain and only one stationary point, which is a local maximum, this must also be the global maximum. Finally, step 6, we write our answer. To produce a cake dish with the maximum volume, squares with a side length of 5 centimeters must be cut from the corners. Let's try another type of problem. We need to design an open-top container with a square base that holds exactly 4 liters. Our goal is to find the dimensions that will use the least amount of material, meaning we want to minimize the surface area. So, we are minimizing surface area, given a fixed volume of 4,000 cubic centimeters and a square base. Steps 1 and 2. Let the square base have side length x and the height be y. The volume, our constraint, is x squared times y, which equals 4,000. The surface area which we want to minimize is the area of the base, x squared, plus the area of the 4 sides, 4 times x times y. Our area formula has 2 variables, x and y. We need to express it in terms of just one. We can use the constraint equation for this. From the volume equation, we can solve for y. Y equals 4,000 over x squared. Now we substitute this expression for y into our area formula. This gives us a of x equals x squared plus 4x times 4,000 over x squared, which simplifies to x squared plus 16,000 over x. The domain is x greater than 0. Step 3, the derivative. It's easier to differentiate if we write 1 over x as x to the power of negative 1. The derivative, a prime of x, is 2x minus 16,000x to the negative 2, or 2x minus 16,000 over x squared. We set the derivative to 0. 2x equals 16,000 over x squared. Multiplying by x squared gives 2x cubed equals 16,000. Dividing by 2 gives x cubed equals 8,000. Taking the cube root, we find x equals 20. Step 4, we check if this is a minimum. Using a sign diagram, we test a point to the left of 20, like x equals 10. A prime of 10 is negative. We test a point to the right, like x equals 30. A prime of 30 is positive. The slope changes from negative to positive, confirming a local minimum. Step 5. Since this is the only stationary point in our domain of x greater than 0, this local minimum is our global minimum. Finally, step 6. We find the dimensions and state the answer. The base length x is 20 centimeters. The height y is 4,000 divided by 20 squared, which is 10 centimeters. So the minimum material is used when the container has a 20 by 20 centimeter base and a height of 10 centimeters. Let's work through one more problem. This one doesn't involve complex geometry, but focuses on a business application, maximizing profit. We are given a profit function, p of x, and our goal is to find the value of x, the number of items, that makes the profit as large as possible. In this case, the function is already set up for us in a single variable, so we can jump right to the calculus. We start with step 3. Find the derivative of the profit function. The derivative of p of x is negative 0.044x plus 11. Next, we set this derivative equal to 0 to find the stationary point. This gives us 11 equals 0.044x. Solving for x, we get x equals 250. For step 4, instead of a sign diagram, let's use another tool, the second derivative test. The second derivative test involves finding the derivative of the derivative. The second derivative of our profit function, p double prime of x, is simply negative 0.044. Here's how the test works. If the second derivative is negative, the function is concave down, and our stationary point is a maximum. If it's positive, the function is concave up, and the point is a minimum. In our case, the second derivative is always negative 0.044, which is less than 0. This confirms that our stationary point at x equals 250 corresponds to a maximum profit. Steps 5 and 6 are to state our conclusion. The production level that will maximize profits is 250 items. This is the number of items that results in the highest point on the profit curve. Let's quickly recap what we've learned today. We've seen that optimization is a powerful tool for finding the maximum or minimum value of a function, which has countless applications in science, engineering, and business. A critical point to remember is that the absolute maximum or minimum value doesn't always happen where the derivative is zero. You must always check the endpoints of your domain as well. We learned a systematic, 6-step method that provides a clear roadmap for solving these problems, from drawing a diagram and setting up the function, to using derivatives to find and test stationary points, and finally, stating a clear conclusion. By applying these principles, you can now tackle a wide variety of problems that ask for the best or most efficient solution. Thank you for watching.